Welcome to Brain Vision.
For this question at the start, we are given this is the equation of the potential. We want to re-express this in terms of x naught, where we have x naught to be equals to alpha over beta. So first of all, we're gonna factorize our alpha. Get 1 over x squared minus beta over alpha times 1 over x. Sorry, the potential here is 1 over x. Now, to get the expression that we want, we are gonna multiply everything by x naught square over x naught square. Right? This doesn't change anything because this is just 1. So what we get, we take the denominator out, we remain outside, but we're gonna bring the numerator in, so we get x naught over x square minus beta over alpha times x naught times x naught over x. Now we see that since x naught is alpha over beta, so this alpha over beta will cancel each other out to get just 1. Right? So this would become just 1. And this is the expression that the question wants us to find. Now next we want to graph the value of the entire function ux. So we can graph it with respect to x over x naught. And using a graphing calculator, we should be able to get a rough sketch of something like that. Now, we want to look and find what is the value of u x naught, basically when x is x naught. Substituting x equals to x naught into our expression here, we would get alpha over x naught square times 1 square minus 1, which gives us 0. And this tells us that at the point where x over x naught is equals to 1, the value of ux is actually equals to 0. So we can basically shift this graph a bit to make it more accurate. The graph would look something like this. Right? And x naught is over here. So sorry, this is not x naught, this is the value of 1, right, where x is equals to x naught. Now we want to calculate what is the value of v, the speed of the proton. Now we know that speed can be calculated very easily from kinetic energy. But to find the kinetic energy, well, this will depend on the initial energy. Right, the initial energy, we are given that the proton is released from rest. So the total initial energy is just the potential energy that it has, which is at u equals to x naught which is actually equals to 0. And so with the initial energy 0, the kinetic energy at any point is the initial energy minus away the potential energy, which is just negative of the potential energy. We already have our previous expression. So this is equals to half mv square kinetic energy. So v is equals to negative 2u over m square root with our expression for u in the previous answer. Right, this will be square root of 2 over m times alpha over x naught square. Right, since we have a negative sign, so the terms inside will be swapped. So we get x naught over x minus x naught over x square. Now we have to graph this using a, you can use a graphing calculator to graph a rough sketch of the velocity. So the velocity curve, again, we're gonna graph it with respect to x over x naught. Should get a rough sketch. This would be a rough sketch of the velocity. Now, what we want to find next is the maximum kinetic energy. Sorry, the maximum speed or maximum velocity, and this will occur only at maximum kinetic energy. Right? And therefore, we will need to find maximum kinetic energy. And remember that our kinetic energy is negative u. So basically we just want to find du dx where the change is equals to 0, so it must be a maximum point. And this will give us the maximum kinetic energy. So we just have to differentiate our potential energy expression with respect to x, and the expression that we should get is this. This is our expression for du dx. We equate this to 0, and we just have to rearrange this a bit. Right, assume that x naught cannot be 0, so we can eliminate, we can multiply by x naught to the right hand side, then we rearrange. Should be able to find x naught is equals to, should be able to find x is equals to 2 times of x naught. And with this we can substitute into our potential energy expression. So u of 2x naught, substitute in x equals to 2x naught, we should get negative alpha over 4x naught square. And therefore our velocity is, which is given as negative 2u over m, must be equals to square root of alpha over 2m x naught square. So this is the maximum speed. Now to find what is the force at this particular point, we know that at this particular point du over dx is 0, and if you were to remember, the force expression due to a potential is negative du over dx, right? Which means that at this point with maximum velocity, the force must be equals to 0. Right? So we don't have to do any calculation for this. But for the next part, now we're going to assume that our proton is released at a different point, right? Our proton is now released at x1. First, we want to locate, right, where x1 is. x1 is equals to 3 times of alpha over beta, which is equals to 3 x naught. What we want to do is we're going to substitute x equals to x naught, x equals to 3x naught into the potential equation. We should simplify and get negative 2 alpha over 9x naught square. So this is the value of the potential at the start. So the initial total energy is now not 0, but rather it is equals to negative 2 alpha over 9x naught square. Now the kinetic energy expression, kinetic energy at any point is taking negative 2 alpha over 9x naught square, right? The initial energy minus our expression for the potential energy. Right, this will give us the kinetic energy. Basically, equate this to half mv squared again. We can get v to be equals to 2 over m of this entire expression. Then we square root the entire thing. Now simplifying this, right, substituting in the expression for our potential energy, should get and so this is our new velocity dependent, which depends on x. Now to actually describe how the particle actually moves using our velocity curve, we see that the maximum speed still occurs when x is equals to 2x naught, because we are just basically, we have an additional constant over here that is added into the expression. Right, but if you were to do the differentiation, this wouldn't affect, and we will still get the maximum speed at this point. But however, the particle is now confined to a region where ux, right, must be less than the total initial potential, total initial energy, which is ux1, or basically this value over here, right? So the expression inside this square root cannot be negative, or else it will be invalid, right? So there's a limit as to where the particle can be, right? And the particle actually now oscillates between x1 and some other point. In more simpler terms, right, this is the potential, and since the particle is being released at x equals to x 3x naught over here, this is the total energy. It can only oscillate around this point to this point and not beyond, because that is the limit of the total energy. And this is described by the validity of this square root term inside as well. And now for part F, we are basically looking at what is this exact value of x over here in which our particle is being confined. Now in the last part of this question, we are simply looking at whether there are any maximum points that the proton will reach if we were to release it at x equals to x naught, versus if you were to release from x equals to 3x naught. Now remember that to find the limits that the particle can reach, we can actually use the kinetic energy, which is equals to the total energy minus the potential energy. And when we equate this to 0, that is the kinetic energy is 0, that is the particle is now stationary. This will correspond to the maximum points where the particle can actually reach, right, or the turning points of the particle. Now in the case for x equals to x naught, our initial total energy, as we have previously calculated, is 0. So basically we are finding the equation u equals to 0. We want to solve for ux equals to 0, right? There is only one solution for this equation of ux, and that is x equals to x naught. Basically, what it tells us is that if it's released from x naught, it will travel on infinitely without any stopping point on the right. So it will travel on towards the positive x direction infinitely. However, if we were to consider the other case where we release the particle from x equals to 3x naught, now our initial energy is not 0 anymore. It is some value, right? Kinetic energy is there's some initial value. But again, we want to solve for when it is turning, right? The turning point, so our kinetic energy must be 0. Now what is this expression? This expression, we will take u 3x naught minus u of x equal to, equate this to 0. Now this expression we have previously simplified. Right, this is the kinetic energy expression. Now the interesting thing is that we can factorize this expression. Factorize it. You can treat it as a quadratic equation, right? Where x naught over x is, say, a variable y. So this is y squared minus y plus 2 over 9. And we will get y minus 1/3 times y minus 2/3. This factorized, and so this tells us that our x over x naught, x naught over x can be equals to 1/3, or x naught over x equals to 2/3. Right? There's two different points where our kinetic energy would be 0. And these points are when x equals to 3x naught, which is our initial starting point, as well as when x equals to 3 over 2 x naught. And what this tells us is that our our particle will be oscillating between these 2 points, where it will stop, right? Because its kinetic energy is 0 and it will reverse direction, and therefore it is kind of trapped between these 2 points. Right, so from our previous analogy, over here it is actually the wrong direction, in that because 3 over 2 x naught is a smaller value than 3, so 3 over 2 is actually on the left, whereas the right turning point is 3x naught. So with this axis as x over x naught, these are the 2 turning points in which the particle will be trapped in. So we are putting the particle starting at this position, and it will simply oscillate between these 2 points.